wait for a few seconds and then I'll start. Yeah, let me share the presentation. Here we go. Yeah, let's start. So today I'm going to talk about strategies of scaling distributed backend systems. My name is Ivan. So a little bit about me. Right now I'm a production engineer at Meta. I am building ML infrastructure. And before that, I had experience in developing highly available backends for large products. And in my free time, I'm building a tool which helps speed up backend development. So I kind of know about different problems and issues that happens during backend development. What we're going to talk about. First, I will tell a little bit about trying to define what is distributed systems, what are they. Then I will talk about some concepts that can help you with scaling and building such systems. And then we'll have a little segue into how to deploy without disruptions. And after that, we'll have time for Q&A. So yeah, that's it. Let's start. First, what are distributed systems? Like, have you ever seen something break in this specific ways? Like you post chat messages or comment somewhere, and you see it not posted once, but duplicated twice or thrice, or some counter jumping around like completely without any reason. Or for instance, you open a page, see some new data, refresh the page, and see old data again. And this is not a simple bugs. This is specific problems that occur in distributed systems. This means that you're dealing with something that needs to handle a lot of users. Yes, so essentially, distributed systems right now in 2023, it's a service that wants to handle millions of users. Like, if you need to ask yourself questions like, what do I want to handle? People from different regions. What if millions of users will load the page at the same time, or if you cannot afford any downtime? Yes, this kind of this means that you want to have a distributed system. But why it is distributed exactly? Before these questions, you probably have one server, one instance, one database that handles just all requests that you need. And that just at the time when you add another instance, at this point, your service becomes distributed. And this state creates sort of unsolvable problems. Like, at this point, you'll have to have some sacrifices. And this is best put into cap theorem. Essentially, it states when you have another partition or instance, and you want to handle failures between these partitions, you would either have to sacrifice consistency, which means having the most recent data, or fail. Like this would be useful when you have financial service, like dealing with transactions, something like that. Or you would have to sacrifice or focus on availability when you want to get any data, no matter how stale it is, but without fail. This is more useful for social networks, I guess. And in this framework, around this theorem, all approaches to building distributed systems are based on. And in the next section, I will talk about problems and concepts that can help us balance in between these values. So what kind of problems we're talking about? The more components you have, the more likely they fail. So essentially, anything can fail. And if we're talking about system which is spread across different regions, most of the time network will fail. Like think about request timeouts. They can happen anywhere between your client and your service, between service and database, between different instances of the service, or the service itself, like instance of it can fail. The underlying database can fail, and what would you have? Well, like people wouldn't be able to add data to your service or read it. So how can we not fix this problem, but how can we bypass them? Let's first talk about load balancing. Now that we have multiple instances, usually we want to have some sort of a service on the front which can handle all requests for us and balance them evenly between different instances. This is usually handled by a load balancer. It takes the requests from clients and distributes them based on region, maybe on load average of your like one instances. So this way, neither client nor services need to care about that. And this also helps if one instance goes down, the client will seamlessly go to another one. So now let's go a little bit deeper into requests. This is on the request level. This is where you have to choose what you want to sacrifice. For instance, if you have some unimportant message like push notification, or you're collecting some statistics, you can afford losing that. And this is where you don't need retries, don't need to care about network failures. You just send the request and forget. But what if you have some useful thing, like again, taking the example of a chat message, or if you have some shop, online store, you want users to put orders, you definitely don't want to lose such requests. And this is where you need to introduce retries, because if network fails, you want to attempt one more. You don't want to force user to do this. And this is where we need to care about request idempotency. Essentially, what this means is if you send the request with same parameters, you should expect the same result. Do you want users to press, if one user pressed button to place order twice, do you want to have two orders from the same user, or you just want to have one? That's the idea. If you create user created order quickly with the same parameter, you don't create another record in database. You just update the existing one. If you cannot track the same parameters, you can add a separate key to the request and say that everything that that is executed with this key falls under the same record in database. So you use this as unique key in your for your request. This approach it's not really widespread because we keep seeing messages duplicated, but this is how you prevent this. Another concept which is really useful. Before we talked about the things that work infinitely with scaling. But some things, even if you add as many instances as you need, some things need to stay in one instance. And for that, we use leader election. Essentially, this is a way to select a single instance that should do work uniquely. For that, we use services like Zookeeper, which provides concepts like distributed locking. This is where one instance can go, ask for a lock, and as long as it keeps it, so like actively keeps it, polls it periodically, it can do work without interruption from other people, from other servers. But if the server or instance, if it dies, it stops polling the log, another server can pick it up. The good example of these tasks would be, for instance, if you have backlog of your orders from customers, you want to process it and send emails for them. You should do it only for one instance. Otherwise, you also have duplication. And the last but not least is caching. Here, think about it in a different way. Like, what if database fail? You want to still preserve at least read-only part of your service. You can cache in memory in the service. It is quite easy to build, but again, we have multiple instances. And if one instance updates data faster than another one, you could have one customer can get to one instance, get the new data, other will get old data. You'll have this jumping around of new and stale information. For some services, it is tolerable. For others, you might think not to do this. And the other solution is just use something like Redis. It is a distributed service. It provides distributed cache. Implementation is pretty efficient, but if, for instance, you'll have a mass network failure, you won't be able to access this cache as well. So yeah, these are the concepts that help you select help you move into the right direction that you want to choose for your distributed service. Like whether you want to have very robust, unfailing, but a little bit stale service, or whether you want to have a strong, consistent database that always return you the last data that your users committed. This is you always will have to choose in between. Now, let's talk about deployment a little bit. These concepts make your backend pretty complicated. The things I showed you on the examples I showed, there would be only 2 instances, but most of the time you'll have a lot of microservices. And with all of that, you still want to release quickly. So what would you do? I think the first focus should go on how we work with version control systems. Think about Git flow. When you create branches and then these branches live for a long time, and then you finish one feature, you want to depend on this feature, you create another branch for that branch. And by the time you want to release it, you'll have to create a separate branch for Q&A, for long testing, and it will be such a hassle to do so. With this approach, trunk-based development, whatever feature you add, you try to merge it as fast and quickly as you can. Like even if feature is not yet finished, but the code required for the feature is needed elsewhere, merge it and continue from the trunk branch. Yes, this would mean that sometimes in the trunk you would have broken features. And this is where you can use feature flux. For feature flux, you need to have some sort of dynamic configuration provider where you can get some Boolean flag which can disable or enable some part of your code base. Like, in this way, you can split a large feature into parts. So, for instance, implementation of storage, implementation of handlers, enable them one by one, and only when they are ready. And, in this way, you wouldn't need to have a different branch for that, and multiple developers can work on that simultaneously. And another thing is that you need to take a slow, gradual approach to deployment. If you have multiple instances, you can use one to release new version, then hold it for a while. Like, for instance, a release new version, enable feature flux, check the requests coming to this canary node are not breaking it, and then gradually, one by one, roll out onto the remaining instances without scaling down them. Just try to do it as slowly as you can. We want to avoid maintenance windows if you have a lot of users. So yeah, that's kind of it. Essentially, distributed systems always introduce drawbacks. There are some instruments how to resolve those drawbacks, but they can only do so much. Something will break. And if you want to learn more about that, we haven't covered, for instance, message queues, batching, and a lot of different stuff. You can try to read this book, Data Intensive Applications. It just it puts everything that I talked about more in detail, and it is just for system design, especially. This is a very great book to read. So yeah, let's have Q&A session. If you have questions, put them into Q&A in the chat. Or just ask if you want.
Hey, Van, I have a question.
Yeah.
So I was thinking, if you have like multiple instances of a service running, let's say,
Mm-hmm.
and multiple services instances parallelly pick a same request to execute.
Mm-hmm.
So how do you ensure idempotency? Do we do it at the application level, or do you handle it at the database level? How we will ensure idempotency in that case?
Good question. In that case, it's probably better to handle it on database level. Think of if it is a write request, think of upsert
Okay.
queries, like insert on conflict to update set, like stuff like that.
Okay.
It's better. Yeah, I didn't tell that in the presentation, but it's better to have as less state as possible in your instances.
Okay. Yeah. Got it. Thanks.
Thank you. I can see another question in Q&A. VY asked, how do you debug find such issues in production? What kind of issues? Like network issues? How can we debug it? Some issues are very easy to track. Like if you see, okay, first of all, to see problems, you need to have, okay, let's talk about network issues first. To see these problems, you need to have observability. You want to trace, log, and have metrics for every request. This way, you could handle timeouts and drop messages, some error codes. Without that, it is I don't know how to do it. And a message duplication. This would require some introspection in your database. If you see comments, if you have like any table, you can just check for the duplication. Yeah, database logs also would help. But
Hey,
yeah,
I have a question, Ivan.
yeah.
Sorry, I didn't mean to interrupt. So my
Yeah, yeah.
question is, after studying about the cap theorem, I think I realized like the cap theorem is really cap or it's line, and that you really only have the ability to choose between consistency or availability, since
Yeah, yeah.
network failures are bound to happen. So it's safe to assume that it's like a 50-50, like you're choosing between just two of the desired characteristics as opposed to the three.
No, I said that we choose between two characteristics. Yeah.
Like,
Like, this guy is also choosing between two characteristics.
that's great. Thank you.
Yeah. Again, either you focus on like if either the easy examples, focus on financial service. You want consistent transactions. You like don't care about failures. You can ask people to retry orders, like if you have exchange, or you focus on availability. That if you have some news service or again like a social network, you don't care if the post is old enough. Yeah. So I saw another question. What kind of backend tools do you use in Meta? Some of them are not open source tools, but they're created inside of Meta. Some of them are can't really talk about, but okay. We use different programming languages and pairing combinations. On backend, we use Python, C++, and recently Rust. Frameworks. Essentially, we use something like that allows us to generate from our internal version from gRPC. Like we have every request are handled through some kind of gRPC framework. But if you can ask specific things because we have a lot of them.
So Ivan, going back on the cap theorem, so looking at this slide, is it always that we choose partition tolerance by default, and then we choose among, between consistency and availability, one of them?
Well, if you don't have partition tolerance, yeah, you can. You don't have to choose.
Okay, but I think most of the systems do have this, right?
Yes. No, yeah, I mean, how to say? If you don't have partition tolerance, you what would you have? You'll have if network fails between partitions, well, you can have separate instances completely unrelated with each other, and then this is called split brain situation when they work independently. Maybe on each of them can handle stuff consistently, but when you want to merge them back, well, how would you do it?
Yeah, makes sense.
So yeah, it's always like that for
Okay.
distributed systems.
Yeah, thanks.
Yeah, but I encourage everyone to read the book. I think it covers more in detail what I've talked about.
Hey, Ivan, I have another question, and this is more like a personal question to you. What
Yeah,
are
sure.
some problems that you've seen come up in distributed systems?
Uh,
Maybe you want like notable ones or unique ones.
uh,
That's okay if nothing comes to mind.
no, this is why I talked about this chat message duplication. This one is personal. Yeah, and other than that, I don't know. Like one thing that I want more people to use is feature flags. That just it is always a hassle to roll back stuff if you don't have them. But it's more like it's not only for distributed systems. Yeah, I get it. Someone is asking where can they find the book. I could give you a link to Amazon, but yeah, you could just buy it from Amazon. Oh, where is everyone connecting from? Are you in Europe? Other countries? Yeah. Oh, New York as well. Yeah, so just this should be available at Amazon. I checked it. It's available for me. There's another question. How do you implement feature flags? Okay, I can send in the chat. There are some like SaaS companies which implement feature flags. One is Unleashed. Other is Open Feature. Essentially, so like you want to have a runtime thing that can toggle boolean values. Anything that can dynamically change configuration that will be more or less quickly distributed between instances. You can use that for implementing feature flags. Like if you have Kubernetes, you can use Kubernetes configs. If you have console, you can use console dynamic config for that. But or you can use solutions that I sent in the chat. Oh yeah, sure. Yes, there's always also launched actually.
Hey, Ivan, is there
Mhm.
scenarios when you want to take your system and turn it into a distributed system? And to like, is there a threshold for like the amount of users or the amount of requests that would warrant a distributed system? And if you have like a rough estimation on like when it's great to switch over to that, and when maybe you may just want to maybe scale your servers or scale some part of your system instead.
Mm, well, usually if you have very optimized service, like it can one instance should be able to handle around 10k of requests, but should be very optimized for that. 10k requests per second. Usually, I think of different stuff. Imagine if there is a point when you don't want to introduce downtimes, when you have so much requests that if you want to stop service for an update, people will complain. Then you introduce gradual rollout, and during the rollout, you will have the second instance. And when you add the second instance, you will need to introduce these techniques to maintain partition tolerance, and then you will have this. You will need to do all of this. So it's not like for me, it's not like a more user threshold. It's more uninterrupted deployment. Or of course you can use distributed locking for that, but it's better to scale when you can. Or if you want, for instance, to if you expect to scale to more users, you can just sell more or do more advertisement, and then you can in advance allow scaling. Yeah, and another point to that, usually it's better to start simply. Like these techniques that I talked about, these are useful only when you're sure that you need to scale. Like maybe except deployment tips, don't think about them until you have the scale. So does anyone have more questions? If not, I think we can wrap it up. If you have any questions for me, this is my social network links. You can ping me on LinkedIn, especially. But yeah, thank you for coming. Thank you for the nice questions. Yeah, see you. Bye.